Okay, welcome to Note Set 3, where we'll get into our first real topic of linear algebra, and that's we will define what vectors are and how they operate. Now, I suspect that you've seen vectors in your physics class to describe things like force, and in reality, the mathematicians have started there when they started thinking about vectors and so forth. They were motivated by the physics use of vectors, but then, as mathematicians do, they abstract the ideas, and we won't really get into the abstract characteristics here. Everything we'll talk about still will have that kind of physical vector feeling to it, with the exception that we'll allow vectors to be higher dimension than just 3. So let's define what we mean by a vector. So it's pretty clear here. We've just got a stack of numbers. So v1, v2 through vn are just numbers that are put into the holding spots in a vector. So, if we have a force, we might have an x, y, and z component to that. That would be a three-dimensional vector, and here we're showing an n-dimensional vector. Now, I do state here that we can allow the numbers to be complex valued, although we will not deal with complex values in this course, but in many applications, it's necessary to deal with complex numbers. But we won't do that. And we say generally put in a column. We can talk about row vectors, where we put the elements in a row rather than in a column. But for the most part, when we say a vector, we mean a column vector, at least in this course. And here I'm pointing out that we use subscripts to identify the particular element. So we might talk about the v2 element, or the vn element, so we can use a subscript to indicate arbitrary size. And as I already said, the number of elements in the vector is said to be the dimension of that vector. And just for purposes of notation, and I don't know if this has been obvious to you in your previous math and engineering courses, but the typeface is very important to conveying information. So authors and publishers have to settle on a firm notational typeset for the various items that we're talking about, and you can often use that to your advantage as a reader as well as a writer to make sure that you are clear what you're talking about. So you can see here that I've used a boldface non-italic lowercase letter to represent the vector itself, and then the elements are italic lowercase non-bold. Now, some books, including the book that we're using for this, use boldface italic. So throughout the notes, sometimes I'll use non-italic and sometimes I'll use italic. It depends. I'm really pretty much a non-italic kind of guy, so for vectors, and we'll see a similar kind of thing for matrices. But sometimes it was easier to just follow, if I was following something from the book, to use their notation. Now, when you're handwriting results, which will be the case for your homework and so forth, unless you want to type it up with equation editor or something like that, which some people do, but you don't have to. But if you're handwriting things, we'll put an underscore under whatever we write. So I'll try to write here, we'll say A and then put an underscore under it. So we'll use lowercase with a single underscore. In a later set of notes, when we talk about matrices, we'll talk about uppercase, and we'll use a double underscore to notate those when we're writing by hand. But in computer typeset, a matrix would be uppercase, bold, either non-italic or italic. Like I said, I prefer non-italic. So we've defined what a vector is, and now we can define how we add two of them together. So we have two vectors, A and B here. Notice that they both have the same dimension. If we have two different dimension vectors, we cannot add them. But when they are both the same, we can define the vector A plus B is a new vector, and its elements are just the element-wise addition of the elements of the two original vectors. So we can see that when we add two n-dimensional vectors together, we get another n-dimensional vector. Now, let's suppose that this last one adds to 0. Does that make it an n-1 dimensional vector? No. It's still n-dimensional. It just has a 0 in that nth dimension. Okay, so that's how we define them mathematically, but we can also visualize them, and this is kind of where the physicist view comes from. We can say that we can define two axes, v1 and v2, and so this vector v will take on the value of 3 along the first axis and 2 along the second axis. And so by looking at that, we can easily visualize what that thing looks like. So by picking different values, we can put this vector anywhere in this two-dimensional plane. So we can see that a two-element vector can be anywhere in a two-dimensional plane. And there's a picture in the book that shows the three-dimensional case, so you should take a look there. So what we're really talking about is, even though we draw the whole vector, we're really defining this point in space. But we think about it as the tail of an arrow goes at the origin and the tip goes out to the point. Now, when we start talking about adding vectors together, we'll have to start thinking about, at least for the purpose of adding them, moving the vector from having its tail at the origin. But in general, we always think of a vector as having its tail at the origin and its point, its tip at the point on the plane that it's representing. So when we look at this, we see that since we have an arrow involved with this, there's a direction and a length. So as we change the point, the length will change and the direction that the vector is pointing will change. And so remember, this is kind of coming from the point of view of physics, where we used vectors to describe forces. So there's a certain strength of the force, but we're also pushing in a certain direction. Physicists also use vectors to describe velocity. So remember, velocity is different from speed. Speed just characterizes how fast you're moving, but a velocity says how fast and in what direction. So it's represented by an arrow pointing in the direction of the velocity, whose length is equal to the speed at which something is traveling. So now let's imagine adding vectors together. So our example here shows adding one vector that's 3, 2 to another vector that's 1, 2, and we get 4, 4. And so this picture over here shows the result of that. So if you drop down here, you get the 1 element, and if you go across here, you get the 2 element, and likewise, you drop down here, you get the 3 element, and you go across and you get the 2 element. So if we add those two together, we get the 4, 4, and that's, out here we can see that drops down to 4, and that goes over to 4. I'll try to clear that off. But we can also visualize this another way, and this is kind of helpful. We could take this W vector here, and if we move it out to here and put its tail to the tip of the thing that we're adding. So you take the tail of W and move it out here to the tip of V, but you don't change its orientation. You don't change its, the direction it's pointing. So just take the whole thing and move it out here. Where that ending tip is actually the tip of the sum W plus V. That's kind of nice. And we can see that it doesn't matter which one we do. So we just move W out to here. We can also move the V, put its tail here, and its tip ends up out here, ends up in exactly the same place. So this tail to tip idea is nice. But if we visualize each of them at the same time, we see that we get a parallelogram where the resulting sum vector is from the origin out to the far corner of that parallelogram. So it's just a nice way to visualize this. So that's vectors, and then we don't want to leave behind our beloved real numbers that we're used to, or if we are allowing complex valued elements in our vectors, we would have to allow complex numbers here. But since we're going to be limiting ourselves to real valued vectors, we will limit ourselves to real valued numbers here as well. So instead of referring to these as real numbers or just numbers, in the context of vectors, we refer to these as scalars. And so obviously we can have an interaction between the scalars, real numbers in this case, and the vectors that we define. So to keep things straight, we'll use a lowercase letter that is italic and non-bolded to represent a scalar. And if you're writing it by hand, you would just not use an underscore. So remember, we would use an underscore to represent a vector, and we would use no underscore to represent a scalar. So I cannot stress enough how important it is to do that. So I will expect you to be doing that in your homework and in your exams, to put single underscores under your vectors, no underscores under your scalars, and we'll see soon in a future note set that you would put a double underscore under any symbol representing a matrix. It will help me follow your thought process, but it will also help you follow your thought process. So I definitely encourage you to do that. And if you fail to do that, I won't take an awful lot of points off, but I may not be able to follow what you're doing, and that would result in taking points off. If I can't understand what it is that you're doing, then you've failed at conveying your thought process to me, and that will lose you some points. But again, don't focus on points and grades. Focus on learning the concepts. So what can we do with a scalar here? Well, we can multiply a vector by a scalar. So we start with a vector A, so I'm bold, lowercase, non-italic. It's got n elements, so this is an arbitrary dimension n-dimensional vector. And if I take that vector A and multiply it by a scalar alpha, what's the effect of having done that? Well, I have to define how that works. There's nothing that comes previously that says, here's how that works. So mathematicians are building the structure that will work. And by work, we mean it will be consistent with previous ideas, but will also extend ideas into new fields or new directions that are useful. So we see that we are changing the elements, but what it really does is it doesn't really change the angle at which the vector is pointing, but it will change the length as long as the absolute value of alpha does not equal to 1. And so if the absolute value of alpha is less than 1, it'll make the vector shorter. If the absolute value of alpha is greater than 1, it'll make the vector longer. And if the absolute value of alpha is 1, then it will leave the length unchanged. And the only change in direction that's allowed is a complete 180-degree reversal. So if alpha itself is negative, it just simply reverses. So here's an example. We start off with some vector v, which is a 3, 2 vector. And if we look at negative 0.5 v, well, the absolute value of alpha is 0.5. And so our vector will be half as long. So our distance here is half the distance of v. And then the other thing that we see is that because our alpha is negative, things are going to reverse 180 degrees. So we are now 180 degrees around there. But notice that any alpha times a vector will lie on the line that goes from the origin to the tip of the vector. So alpha v will, regardless of what alpha is equal to, will lie somewhere on that line. And what if alpha is equal to 0? Well, that is the vector that is just the dot right at the origin. So that vector, from visualizing it here, would have a length of 0, but it still lies on that line. And so we can say alpha v, the set of alpha v for all alpha, forms a line through the origin. So we've defined addition. It's pretty straightforward to then define subtraction. So it's also defined element by element. So if I take a minus b, I'm going to form elements a1 minus b1 all the way down to an minus bn. And, well, we just saw that multiplying by a negative number flips the vector. So we can think about subtraction being nothing more than first flipping b and then adding those two results. So that helps us visualize what we should get. So if we're doing v minus w, we take w and we flip it. So here it is. Same length, just pointing in the opposite direction. And now we're going to add them together. And so, here's our parallelogram view. Either way, we can add v to negative w, or we can add negative w to v. Either way, we get this vector that is, in this case, horizontal. So that would be v minus w. So it's important to be able to quickly visualize what the sums and differences of various vectors look like. So what we're doing here is building the arithmetic structure that vectors must live within. So we've defined vector addition, we've defined scalar multiplication, and together those things will also define vector subtraction. But in general, we can just talk about vector addition and scalar multiplication. Those two things handle everything that we've talked about already. So suppose we have three vectors in the same dimension, x, y, and z, and we've got two scalars, alpha and beta. We can state the following properties that must hold. So commutativity, and these properties carry over from what you're familiar with just regular old real numbers. So it doesn't matter whether I add x plus y or I add y plus x, I get the same answer. It doesn't matter whether I multiply from the left or multiply from the right, I get exactly the same answer. Now we have associativity. It doesn't matter if I first add x and y and then add z to that, or equivalently add x and z together and then add y to that. Either of those are the same. And then the same kind of thing with, if I'm multiplying by scalars, I can first multiply by the scalar b to get a new vector and then multiply that vector by alpha, or I could first just multiply alpha and beta together to get a new scalar, maybe call it gamma, and then multiply that gamma times x. Both of those will give me the same exact result. So commutativity, associativity, you're familiar with those. That's just how real numbers work. Distributivity works exactly as you are used to. So I can add x and y first and then multiply by scalar alpha, or I could multiply scalar alpha times vector x and multiply scalar alpha times vector y and then add those two results together. And it also works, well, let me back up. So in other words, I can distribute alpha through a vector sum. But I can also distribute this vector x, distribute it through a scalar sum. And then we have the idea of scalar unity. So the number 1 times any vector x just gives us back x. So these are the things that mathematicians worry about. They seem trivial, but they nail down the structure and make sure that everything works as we expect. And there has to be a 0 scalar, such that when I multiply 0 times a vector x, I get back 0. Now, a word of caution here. This 0 here is a scalar, and it's a little hard to see the difference in the notation. This 0 here is actually a vector. So it's a vector with every element set to 0. So it's difficult to see that subtlety in the notation. And now this is the biggest idea in this set of notes, I'd have to say. Linear combinations of vectors. This is the root of everything that we'll be doing. So focus on being able to visualize this idea. What we're really trying to do is build a new vector from some given set of other vectors. So suppose we've got m vectors. We're not saying what the dimension is here, but they all have to have the same dimension. And then we define the idea of a linear combination of these vectors is just a weighted summation. So we take each vector, and we're summing from k equal 1 to m, and we just put a coefficient alpha sub k out in front. So this literally is alpha 1 times v1 plus alpha 2 times v2 all the way out to alpha m times vm. And that sum is what we'll call, at least here, v. So, and then we can take the same components, the same building blocks, pick a different set of coefficients, so form a different weighted sum, and we'll get some other vector, which we'll call u. And so the interesting thing here, one of the questions that we'll be looking at is, given a particular set of vectors, what can I build this way and what can't I build this way? Will I be able to build any possible n-dimensional vector, or is there only some subset of vectors that I can build for this given set of vectors? Or flip that question around. If I want to be able to build any vector in my in n dimensions, what conditions do I need on my set of m vectors to be able to do that? And so that's actually a big question, and we'll spend a fair amount of time talking about that in future note sets. So I'm just pointing out here that we're making two different vectors from the same ingredients. So I like to think of all this vector stuff as cooking. So the ingredients in my pantry are the vectors v1 through vm, and the alphas and the betas are the differing amounts of each of those ingredients. And so changing the quantities of those ingredients, I could get something very, very different. And you know, if there's one recipe that doesn't call for v sub m, well, make the coefficient alpha sub m equal to 0, and we'll keep that out of the linear combination. So this idea of building out of the same ingredients but just different amounts of them is a huge, huge idea in this field, and we'll come back to that. You know, from now all the way to the very end of the course, that will be key to things that we're doing. So once we have this idea of linear combination, we can look at 4 special cases where we combine just two vectors. And so these just show the different ways that we can use this idea of a linear combination to cover some very special cases. If we let the coefficients just be equal to 1, we're covering the case of just adding 2 vectors. If we let one coefficient be 1 and the other coefficient -1, we are subtracting. If both vectors have coefficients that are 0, then both vectors get zeroed out, and a 0 vector plus a 0 vector is 0 vector. So that's another case. And then we might just allow one coefficient to be non-zero, but the other one is definitely 0. And so we can end up with a result that lies along the line. So I should say, when I talk about the direction here, I should put quotes around it, because we do allow pointing in the opposite direction as well. So suppose I have v equal to 4, 2, and w equal to -1, 2. Can you visualize what these vectors look like on this set of axes? And so I would encourage you to pause the video here and see if you can visualize where those vectors are, and then come back, restart the video, and move on. So give it a shot. Pause here, and I'll wait for you. Okay, so hopefully you took a little time to draw those on that set of axes. And so you can see I've shown the v vector over here and the w vector over here. So v vector has a point out to here, and the w vector has a point out to there. And if we look at the first special case where both coefficients are 1, we get the sum. And so here is our vector out to this point. That's just v plus w. And if you do that numerically, you'll see that the result is 3, 4, and that's consistent with this. The position of that dot that came using the parallelogram rule. Here's our second special case. Remember, subtraction, we can form -w and then add the results. So we're adding along the parallelogram to get out to this, and we get 5, 0. Our third special case, if each vector is multiplied by 0, so 0 times w puts us right at the origin, 0 times v puts us at the origin, and so 0, 0 plus 0, 0 gives us 0, 0, and so we are at the origin. So that's a special case. And then the fourth special case, we fix the coefficient of w to be 0, and we're left with just this. So I can create anything on this line. I could make it go out to that point, this point, not that point. Let me try to clear that up. Let me erase that. Okay, yeah, so I can come out to there, I can come out to there, I can come to there. So any of those are possible. So the key here is that result lies on the line that lies, the line upon which v lies. And then we have our general case. And so we can pick any c and we can pick any d. And so for this example, for these two particular vectors, since they have a certain coverage, right? This one points off in this direction and this one points off in this direction. We can actually choose c and d to get any vector in the plane. So there is a condition where we can specify a v and a w where this is not true, but in this case it is definitely true. And so Let me clear off those lines for a second. So these dashed lines, these blue dashed lines, show you the lines upon which I can create any scalar multiple of v will lie on somewhere on this line, and any scalar multiple of w will lie somewhere on this other dashed line. And so if I properly pick my c and my d, I can pretty much get anywhere. So if I pick a c that will take v from, instead of being this long, we'll take it out to here. So that'll be a positive scalar that is, maybe about 0.3 or so. And then I can take w and scale it to being over here. So it's in the opposite direction of the original w, so I know it's going to be negative. So in this case, the d value up here will be negative. And it looks about the same. Looks about the same length as w, but it's hard for me to tell. But so maybe 0.9 or 0.8 or something. And so then if we add those two together, doing the parallelogram view, we get this dot. And so the new vector is that. So in reality, for two vectors that don't lie on the same line, we can create anything. And what we've really done in this case, because these two original vectors are at right angles to each other, you can really think about what we've done is rotated our axes. And so we have a new set of axes, and you've probably seen that in some of your previous coursework. So a lot of what we'll be dealing with is, if I've got two given vectors and I want to use those to create some other desired vector, how do I find the c and the d values that I need to build the desired vector? And that's one thing that we're going to look into and learn how to do. So here are some challenge questions, and I would encourage you to pause now and give some thought to each of these challenge questions before going on. When you come back to the video, we'll talk about each of these cases, but I would encourage you to think about them before just watching through. Okay, hopefully you had some success in thinking about those things. So let's think about, we've got some vector u. We'll assume that it's not the zero vector, otherwise it's kind of a boring question. But you might want to think about what happens when you have c times the zero vector. But assuming that u is not the zero vector, what does this give as we let c take on all possible values? We've already talked about how that will give us a line through the origin. And it doesn't matter the dimension of u. So when u is two-dimensional, we can draw two axes. When u is three-dimensional, we can think about a three-dimensional space with an x, y, and z axis. But what about 4 dimensions, or 5, or 6, or however many, 1,000? You can't picture those. You can't draw them, but you can kind of think through it. So think about 100 dimensions. And there's some vector in that 100-dimensional space. And if you look at c times that vector, you're going to have a line that's coincident with that original vector and going through the origin. So we've defined a line in n-dimensional space. So what about if we have two different vectors, u and v, and now we can combine them in any linear combination? Well, two vectors will define a plane. So imagine taking two pencils and anchoring their erasers at the origin, and then laying a piece of paper, so that a stiff piece of paper, so that it lies flat against the sides of of the pencils. No matter how you orient the pencils, you'll be able to put your piece of paper so that it lies flat on the edges of each pencil. That's the plane that that each of those vectors lie in. So you give me two vectors, and there's going to that aren't on the same line, and there will be one plane that's defined by those two vectors, and I can create any vector in that plane by just properly choosing the coefficients c and d. What if we have three vectors now, and presumably they don't line up in some way? So now we can get a three-dimensional space. So take three pencils, kind of put the eraser of each of them at the origin, and just kind of have them pointing out into space. That will kind of define three-dimensional space, and you can have those three add a weighted addition and have them result in any vector that you want by properly choosing C, D, and E. And so we get a three-dimensional space, and we'll be using this symbol for our spaces. The fancy R there stands for real. That's the real number line. But the superscript 3 is not cubed in this case. It's telling us three-dimensional. So three-dimensional real space, or R3. Now, notice that in each of these cases, the 0 vector is always included. So the line goes through the origin. The plane goes through the origin. The three-dimensional space, I don't say through the origin, but it really is a three-dimensional space that goes through the origin, or at least includes the origin. Now, on all of the comments above, I've had to add something in to say, well, at least as long as U and V have this characteristic, or at least as long as U, V, and W have this characteristic, then I will have these results. So what are these characteristics? What are these conditions? So, pause the video, give it some thought, play it back, listen to what I had said earlier, and see if you can think through and visualize the conditions we need for this to actually be true. Okay, so hopefully you're back. I have no way of knowing whether you went away and thought, and if you did go away, I have no idea how long you stayed away. But anyway, the conditions are that the vectors can't lie on top of each other, or lie on the same line, or in the case of U, V, and W, they can't all lie in the same plane. So we'll have some terminology to define or describe that condition later on. But for right now, if I had one vector, let me just back up here. So if I had over here U that went like this, and V that also, it's kind of hard for me to draw that here, was aligned with U, then their linear combinations would not form a plane. Linear combinations of those would still just form a line. So you have to have some diversity of these vectors to be able to get these results. Okay, let's look at some exercises here. We've got some specifics. We've got a V, we've got a W, we've got a B, so three different vectors. And we're asking, how do I pick a C value to multiply V by and a D value to multiply W by to result in this given vector B? Seems like a simple problem, but this is really at the heart of much of what we'll be doing. And so if you can get a latch onto this, the ideas we'll be talking about that are a little more abstract will be much easier to think about. So again, I'll ask you to pause here, see if you can make some headway on this. If you can't, it's not a big deal, but really trying and then seeing is much, much better than just seeing. So I do want to point out before we get into solving this problem that when we apply math to engineering, we're really doing two different things. So the first is modeling the real world. So we need to come up with some sort of model, and what we're doing with that model is trying to express mathematically something about the real world. And so it may, the reason we call it modeling, it may actually capture everything about the real world, or it may capture just the most important parts. So that's sort of, consistent with the idea of modeling. So when we build a model car, obviously the engine doesn't run, but it might look like the engine, and maybe that's good enough for us to answer some question about, how big of a garage do we need to build this car? We don't really need the engine to run to answer that question. So anyway, modeling allows us to formulate the problem mathematically. And then once we've formulated the problem or modeled the problem, we then solve the problem. And so that's the computational part of this. And to be a good engineer, you kind of need to be good at both of those. Although some people will focus more on one than on the other. All right, back to our exercise. Find two equations for the unknowns c and d so that the linear combination cv plus dw equals the vector b for these given vectors. So we're only really going to do the modeling part. We're just going to set up the equations. That's why we say here find two equations for the unknowns. It doesn't say find the unknowns. So what we want to do is find c and d such that this is true. So here's the abstract way of writing it. CV plus dw is equal to b. But now we plug in the specific values that these vectors have, and we have c times 2 minus 1 and d times minus 1, 2 must be equal to 1, 0. And so if we look at this, using our what we've defined already as far as scalar multiplication, we end up with c being moved in here and a negative c being moved in here. So now we no longer have that there. And we've got a negative d in here, and we've got a d in here. And then we add them together. So we're going to have c plus a negative d, and that must be equal to 1. So there's our first equation. And then we have negative c plus 2d, and there's our second equation. And that's equal to 0, which is the element over here. So that's just exploiting the idea of scalar multiplication coupled together with vector addition. And so that's where we're going to stop this set of notes. You may notice that I've put little arrows at the end of each slide, and I've put a stop sign at the end of the very last one so that I don't just blow past the end of the slide and then have to say, oh, I guess that's the end and we'll see you next time. So this is the end, and I will see you in the next set of notes.